And for this case, okay, delta L is also known as the axial deflection. Why axial? Because delta L, the change in L, right, is parallel to the what? Is parallel to the centroid. Okay, the centroid axis. Okay. Now, how is this relate to stiffness? Okay, so how to relate? Okay, stiffness in structure analysis. Okay, how to relate? So we know that stiffness, the general notation for stiffness, okay, is K, and the units is in Newton per meter. Okay, it's in Newton per meter. So usually we talk about stiffness, we relate to springs. Okay, so relate to spring. So what do we mean by relate to spring? So if I have a spring, this is our spring, and the spring have a certain thickness K. Okay, and I'm going to draw the spring a bit longer. And now if a spring okay, we apply a load, and the load P is here. Okay. And if you take the distance, the difference in the distance between the two of them, this is your delta Y. Okay. So the spring stiffness K is equal to Py over delta Y. Okay. Or we can express this to be the load Py is equal to K delta Y. And mathematically, what does it mean? Okay. So if this is your delta Y, this is your P, and it's going to have a linear relationship. This over here is your stiffness K. Okay. So now looking at this equation, so this is our equation number 5. Okay. So from equation 5, we know that Py is equal to K delta Y. Okay. And we know that delta Y over here is also the same as delta L. Okay. And this is from equation number 4. Okay. So when we substitute equation number 4, okay, so we know, note, hold on, let me rewrite, note that delta Y is also equal to delta L from equation number 4. Okay. So therefore, Py is equal to K. So delta L is equal to what? Delta is equal to Py L naught over AE. So you cancel this is equal to 1, you cancel this. So stiffness, so therefore, stiffness K is equal to AE over L naught. So the stiffness of the structure is a function of the cross-sectional area, Young's modulus, divided by what? L naught. Okay. The higher your cross-sectional area, the higher your Young's modulus, the smaller your L naught, the stiffer is your structure. Okay. However, this expression is useless for buckling analysis. Okay. Okay. So this expression is useless. Okay. Why is useless? Okay. Why is useless? Okay. Why delta L is equal to PL naught over AE, and stiffness K is equal to AE over L naught cannot be used for buckling is because the deformation is along the axial axis or parallel to the centroid. Okay. So what do I mean by that, right? So remember the green line that I've drawn, right? We have this, right? We have the structure earlier, and then this green line we have drawn, right? So when we apply the load, right? When we apply the load, the deformation, okay, the deformation is along the centroid. So that if I put a load P down here, right, you can see the deformation is acting along the what? Centroid. It's along the centroid or parallel to the centroid. Okay. So you can see that delta Y is parallel or along the centroid. You can see that, right? However, in buckling, okay, in buckling, deformation, or I will write down here elastic deformation, is not along the centroid. It's not along or parallel to the centroid. And I believe you all know that already. Okay. Why delta L is negative? Okay, so delta L if you look at delta L, right, it's negative down here because the change, the original is longer than the final, so it's negative. So when I put into equation number 4, right, when I put into equation number 4, left hand side and right hand side, the negative both cancel. Chloe, does that make sense for you? I do apologize, it's like 10 minutes late, okay? Okay, which equation is marked as equation 3? Did I skip equation number 3? 1, 2, yeah, you're right. I lost equation number 3. Yeah, just ignore equation number 3, just go to 4, okay? Yeah, I did not. Okay, I know which is equation. This is equation number 3. Okay. Right. So in buckling, elastic deformation is not along or parallel to the centroid. So how does it look like? Okay. So deformation pattern. For buckling. So in buckling, usually what will happen is the structure is very slender. Okay. So over here, you have built in. Okay. And then we have our centroid again. And then we have a P, PY, which is our axial load acting along the centroid. So the green line that drew, this is the centroid. Okay. And then we also have over here our A. So A down here represents our cross-sectional area. And then we have a distance from here to here. This is still our L naught. Okay. So in buckling, the deformation occur this way. So I'm now going to construct two axes now. So this is now known as my y-axis on this graph. And I'm going to draw another straight line. On this graph. This is our x. Then I'm going to sketch in red the deformation pattern. Okay. So this is the deformation pattern for buckling. Now this is exaggerated, okay? So this is now our what? Deformation pattern.